1 is equal to V naught 1 by 2 pi cube dSE by mod of grad E means gradient of E K dE divided by 2E minus small e minus 2EF naught, where E is equal to h cross square k square by 2m. So you can see this. Now where the volume element, where the volume element dk is separated into an area dSE on the energy surface, on the energy surface, and a component dk perpendicular normal to the surface, normal to the surface. That is, as I had mentioned you earlier, that is, this dk we can write as the product of dSE and dk perpendicular, and dE is equal to gradient E dk perpendicular. This is quite obvious. This gradient E, k means rate of change of E as k changes, and k changes normal to the energy surface. Therefore, this is dk perpendicular. That is, dk perpendicular is equal to dE divided by gradient E. And therefore, now you can understand this particular equation. Next, now I just forgot to put the equation number here. This equation I provide equation number 14 to this. Now, so now we perform the integration. That means we take up equation 14 and perform the integration. I show this equation once again. Now we are performing the integration over this equation 14. So by performing we obtain, you can also practice it, try it at home, this you will get. So by performing the integration, we obtain 1 is equal to, what do we obtain? 1 is equal to V naught Z EF naught plus H cross omega d, these are the two limits, dE divided by 2E minus small e minus 2E F naught. So this is equal to 1 divided by, so half V naught Z EF naught. Mind you, Z or Z stands for the density of state. So density of state at the Fermi surface, log small e minus 2H cross omega d upon small e. So this I give equation number 15, or we get E is equal to 2h cross omega d divided by 1 minus exponential 2 upon v naught z e f naught. This I give equation number 16. Now, in the case of weak interaction, now in the case of a weak interaction, this V naught Z E F naught is much smaller as compared to 1, and this would imply the small e to be nearly equal to minus 2h cross omega d e raised to the power minus 2 divided by V naught Z E F naught, that is E is equal to E minus 2 EF naught, means small e is equal to E minus 2 EF naught is negative. So we get equation number 17. So this is equation number 17. E is nearly equal to minus 2h cross omega d e raised to the power minus 2 by V naught Z E F naught. For this I have put equation number 17. That means this small a is less than 0. That means it is negative. Here we get the negative value. So now this also brings our discussion towards an end, because this is an all important result. It clearly shows that there exists a 2 electron bound state whose energy is lower than that of the fully occupied Fermi C by an amount small e, given by E minus 2 EF naught. That means the ground state of the non-interacting Fermi electron gas becomes unstable when a minute attractive interaction between electrons is switched on. So with this, we come towards the end of our discussion on Cooper pairs. So viewers, after having a long mathematical session with you, now I would like to conclude this lecture with the following takeaways. Number 1, the ground state of the non-interacting free electron gas becomes unstable when a minute attractive interaction between electrons is switched on. Number 2, this instability leads to the formation of 2 electron bound state whose energy is lower than that of the fully occupied Fermi C. Number 3, in reality this instability leads to the formation of high density of such electron pairs, so-called Cooper pairs, via which the system tries to achieve a new lower energy ground state. Last but not the least, the wave function that we have taken up in our discussion has got the spin part also, so that the total wave function is antisymmetric in nature because the electrons are fermions. And therefore we can say that the Cooper pair is comprised of two electrons of equal and opposite wave vectors and opposite spins. With this, I conclude my lecture, viewers. Goodbye. Have a nice day.